Testing the audio. It should be a 5-second delay. Okay, I think the audio is working. I've had a few troubles this morning. So let's look at this one. Um, I think the audio is working. All right. All right. So let's see. I may not have time to complete the whole thing. I was planning to use the other computer because it behaves better, but this one is what I've got. Hey, cool. I can just wipe that out. So, just bear with me as I. Oh, I need the problem statement. Okay. Shoot, where is that? Might be able to put it right over the other word. Nope. Goes down underneath it. So it's pretty obvious that the writing is going to be very delayed here. So I will probably be fairly frustrated with that. But we're just going to try to work our way through it anyway. Okay, so it says if the arm rotates with a constant clockwise angular velocity of that, determine the force on the arm OA. This is the arm right here. Determine the force arm OA exerts on the smooth 4-pound cylinder when this angle is 45 degrees. Okay, so the first thing we've got to do, we've got to recognize we're in polar coordinates. And if you look back, you have 6 things that you need to do. Those are the 6, by the way. You need to know those, and he's stating at 45 degrees. This one's never really specifically in the equation. It's just implied there. And you need the accelerations. Here's why. Let me see if I can draw a free body diagram here of the thing. So there's B. This is B. And there's this wall right here. And so actually, as it's pushing on it, it's the wall, okay, the wall is pushing this weight on it. The arm is this thing, and it's pushing this weight on it. The actual thing itself weighs 8 pounds, 4 pounds. It weighs 4 pounds. And that's essentially all of the information on it. As far as the forces go, I guess I have to put this as a force. This is the force he's asking for. So, of course, back down this way, this is part of the problem that I do not like here. This is the location O. So you have a R coordinate and you have your theta coordinate. So what you're going to do eventually is you're going to work yourself out to some of the forces in the R direction, mass, which is the mass of the thing, it's 4 divided by 32.2 times the acceleration in the R. And then you're going to basically come down and solve for that. You're going to have to do both, and the reason you're going to have to do both is because of this silly thing right here. I guess both the weight and the N are going to cause you to have problems here. The first thing you need to do, this is a touchscreen. So the first thing you need to do is figure out the R value. Okay, here's your R value. Well, you got a triangle, and the cosine, that's not a C. The cosine of theta, where this is theta, is going to be that 4 that's out there divided by R. So you're going to have to flip these around and say R is equal to 4 over cosine of theta. And, you can do that, but you can also go down the path of looking at this as a secant function. So I'm going to check real quick and see if I installed. Looks like I did. Okay, so I have this. This is a free package out there. It works very, very well. Been around for a long time. Nicely done. Can do. See, I'm having all sorts of visual artifacts with this crazy thing. I think it may be that the graphics driver is why the thing is so slow. And this is supposed to be a fast one, so that'll tell you something. Okay, so what we have, let's go back to the thing. We have, and I can write to the right over here, so 4 times SEC theta. Now, what I'm going to do, before I go any further, I'm going to integrate Okay, the expression is, well, I guess I could put the 4 in there. Or I can just do this. Secant of, and in this particular case, if you look, the variable he wants to integrate with respect is x. I'm sorry. I want to differentiate. Okay. Okay. So this tells you I want to differentiate the expression with respect to that variable for how many times? Just one. Secant x, tangent x. Okay. That'll make it fun for the next one. And since that was 4, secant tangent. Now, I can go back to this. And you see that 1 right there. I can just, let's see if I can go back here and just take its derivative twice. Oops. This is one of the things. I think you hold the shift key down and hit enter. Oh my. Okay. That's not fun. Secant tangent squared. Okay. Yuck. Oh, but wait a minute. There's... Okay. I have to... Let's delay this thought for one more point. Okay. There's one thing I forgot. Okay. Let me go down with this derivative. Okay. I'm going to write over here, and then I'm going to erase. Okay, so I've got dr dt. Well, I'm just going to leave the 4 off for right now. The secant of theta dt, but I have to do this. So in fact, what I actually have here is I have a theta dot stuck there. So I need to be more particular about this because I need to carry these theta dots will end up, because I'm not taking derivative with respect to theta, I'm taking derivative with respect to time right here. So now let me come back and run down this one path. And that path is r double dot is equal to derivative of with respect to time of, and I'll leave the 4 out again. And so now I've got 3 individual terms. So I'll take the derivative of this one times these 2, derivative of this one times those 2, derivative of that one. So the first term, I'm going to have this. The second term, I'm going to have this. But we have to remember, it's still with respect to time. And then the third term, I'm going to have this. Now, what happens is we already took this derivative, so that term's going to be theta squared. Why? Because we've got secant theta with respect to theta and d theta d time. This becomes theta dot and adds one more to that term. So now you look back up, you'll see a secant tangent squared plus, now the derivative of the tangent with respect. So what I'm going to do here I'm going to recognize that that is that. So take a 2-step backwards. And now let's go back to this equation. And I want to do a tangent. And I only want to take its derivative once. Oops, again, I got to watch out. Shift, enter. Secant squared. Okay. So this becomes the secant squared of theta. Oh, and there's already a sequence, so this one becomes theta, and then squared, and then plus theta double dot secant theta tangent theta. Oh, geez. Let's see. I think what I'm going to have to do is slide some things out of the way. Here's what I'm going to do. I don't have enough space for this. So what I'm going to do is take this space, move it down in there. And now that we've been through that, sort of take that out and take my time and write this crazy thing down. First thing first, I'm going to take that term first. I have to make sure I include my 4 again. Theta double dot, and I have to be patient because I'm using the computer that's supposed to be better, but it's not necessarily better. And then I'm going to go after, I don't know which term I should go after first, but I think what I'll do is just go after this term next because, and since I didn't put 4 around the whole thing, I have to do 4 times each one of these terms. Okay, so I got that. And then I got a 4 again times this term. Oops, there. So with all that, good grief, that's ridiculous. Let's make sure that we've got this copied. I put my 4 in there, put my 4 in each of the spots. I have this term right here. We should have this term right here. And I should have this term sitting right there. And I think I do. So at this point, I don't know whether to even save any of this or just move it out of the way. So I guess what I'll do is I'll try to just save it way far out of the way. I'm moving it way farther. I have no idea why that showed up. Okay, so I have that. He told me it has a constant angular velocity of 1.5, and if it's constant, that term is 0. So what terms end up being 0 in here? This term is 0. That's it. So, okay, so let me rephrase this and change the way I'm actually saying this. So now, what I need to know from this is R evaluated at theta is equal 45 degrees. because this is what he asked for. He wants to know the information when theta is 45 degrees. So what you have is r is equal to 4 secant of 45 degrees. Then you need to know, you need to know r dot when theta is equal to 45 degrees. Why? Because that's what he asked for. Well, the theta dot at 45 degrees is 1.5 because it stays 1.5. So it's 1.5 times the secant of 45 times the tangent of 45. And this last one is r double dot when theta is equal to 45. And that is 4 times 0 times the secant of 45 times the tangent of 45. I'm going to write down underneath here because I've got this stuff over here. 4 times theta dot, which that's 1.5, and it's squared because you see the square right there. And then it's secant of 45, tangent squared of 45, square because it's square right there. And then when I pick up this, which is plus 4 theta dot squared, again theta dot's there, 1.5 squared, secant to the third of 45 degrees. Okay. Now, remember your final goal is to do this with the free body diagram over here. So let's sort of look at what AR is in A theta. Remember, these are the components of the acceleration. AR times UR, where that's the base vector, and A theta, U theta, which that's that. Turns out that the AR is R double dot minus R theta dot squared, and the A theta is R, and we got an advantage here, theta double dot minus 2 R dot theta dot. And you can look back in the book and you'll see that. Or you can look online. You'll see that these are the coordinates. Now what you need to do is, and I should take a minute and calculate each of these. And let me do that real quick. It'll take me a minute. And I have no guarantee that I'm going to be right. I actually may use my calculator to do this because I do not have MATLAB on here. Okay, so I got 5.6 or 5.7. Let's just say 5.7. I'm going to drop some of the digits. And then 4 times 4 times the secant of 45, tangent of 45, and then 1.5. So that's 8.5, 8.4. And then the last one, which is awful, okay, so that term's gone, so I don't have to think about that one. That shortens it. 38.2. Now, if we combine this. Oh, I meant to say that. Oh no, we're in that mode where it's not listening to me. It won't change pins again. Okay. So we're stuck in this color and this pin type. Okay, so if I take this and I take these and inject them into here, I'll get acceleration R is equal to 38.2, not 4, or maybe it was 30. Anyway, minus R, which is 5.7, theta dot, which is 1.5. I better add the extra terms on here. Well, they're in the calculator. Well, that first term is just going to be 0 minus 2 times R dot, which is 8.5, and then theta dot, which is 1.5. Let's make sure I did all that right. 38 came from here, there. Okay, and the 5.7 came from there. The 1.5, oops, that's got to be squared. Is there any other? I forgot the squared there. Okay, so I have these extra digits in the calculator. I'm not sure that 38, about 25. I'm just going to say, I'm going to be really bad and drop all the digits and just say I got 25 here. That's bizarre. I'm getting 25 here as well, even with the digits. Maybe that's because it is 45 degrees. Well, let's think about that for a minute. Yeah, that makes sense. Okay, so the ball itself can only go up and down this incline. So it can technically only accelerate up and down this incline. So that means it's whatever value is here is going to be here. I think that's bizarre. It's a bizarre problem. Okay, so now the only thing you've got is this diagram. Oh no. So you have your values of 25. You have your masses here. So now what you've got to do is you've got to break it into your components. Okay, so you've got your 4 pounds and you've got your N. Technically, you're going to have 2 equations and 2 unknowns. This is one unknown, that's the other. So you're going to have to solve a set of equations here. I don't know how they're going to look right off. But the beauty is it's 45 degrees on both of them. So what I'm saying is, if I look at some of the forces in the R direction, this being the R direction, I get minus 4 over square root of 2. It's coming at you. Then you get the N going the other way. N over square root of 2. Why square root of 2? Cosine of 45 equals sine of 45 equal 1 over square root of 2. And that's equal to, those are the only 2 forces in the R direction. You got that component and this component. Those are the only 2. And then you get the mass, 4 over 32.2, and you get your acceleration, which is 25, roughly, with some digits. Then you sum the forces in the theta direction. You're only looking at the forces in the theta. By the way, that was the mass. This is the acceleration. What do you have in the theta? Well, first of all, you got your force F. And you got this component coming back at you. minus 4 over square root of 2. Y square root of 2, same thing. And then you got the minus your n over square root of 2. And that's all you got there. So 4 over 32.2 and 25. Okay, at first glance, I thought I was going to have to make a matrix, but if you look at this thing right here, you don't, because there is no f in here. There's no f in that equation. So this means you can stop or start or whatever and immediately say n is equal to square root of 2 roughly times 4 over 32.2, 25 and change, which is still in my calculator, or I can at least get it out of there, and then move the 4 over. Okay, so let me put my pen down and do this. Okay. This shouldn't be too hard. One wouldn't think it would be too hard. Hang on, I'm having to recall things. Here we go. Okay. So first, I'll do the square root. Okay, then I gotta add 4 when I get done. 8.47. Whoops. I get n is equal to 8.47. I carried the extra digit in there. Now that I have that, I should be able to grab this, move it to the other side. 4 over 32.2, 25.5, plus 4 over square root of 2, plus n, which is that, over square root of 2. And I think that's it. Now I'm just redoing this equation right here. So okay. Add that, and then 8.47. And I get 11.98 on mine. Come on. Here we go. I got a touch screen, so make my way. Oh, it only just it doesn't give you any intermediates. So he says the force is 12 pounds. Is that what I got? Oh, here we go. So again, you're in polar coordinates. The biggest annoyance was that, followed by the annoyance of the derivatives. The first derivative was not that bad. The second one was not that good. Then you had the calculator strain of inserting all the numbers, and I guess I did a fair job there. And then you needed to take these and insert into this set of equations. And once you did that, you basically got the accelerations as a number. And I threw away the digits. There should have been a half in there. The next phase is where, okay, so you could break this into two components. This is kinematics component, which is basically finding the accelerations, which is what you did. Once you have the accelerations, you're over here in what they call, and I guess it makes sense, this is the kinetics part, which is basically using this, let me put this down, using those forces, using those accelerations to find the forces. And so at that particular point, you're moving from chapter 12 into chapter 13. And not that the chapter numbers really mean that much, because they could be different chapters in different books. But again, you're moving to the next phase, which is using the free body diagram, or making a free body diagram, then using it about the forces. And then all you're doing is you have the accelerations, you copy them over right there and right here, ensuring making sure you have the right mass associated with it. And on the left side, you're just creating a force diagram. In other words, you're getting the forces from the force diagram, and then you're just substituting back and getting the number. Let's look at the other problem. In a minute. Let me find where's my mouse? There it is. Okay. What? Oh. Whoa. This one. But I only have a few minutes. So maybe I'll delay that one until Monday and solve that out on Monday. Let me go back to my live stream real quick. How's the live stream doing? It says it's doing okay. And my broadcaster seems to still be doing okay. The volume is still there. So I think what I'll do is I'll broadcast that solution from the classroom, and I'll open up the last week on Monday itself. So I'm going to draw this to a close real quick.